This is a demonstration of the steps to create model-based technical data of an existing part. The problem is, a replacement part is required but cannot be obtained through the normal supply chain. One solution involves the use of 3D scanning to capture the shape of that part in order to create the model-based definition for the technical data package. We will see how to prepare the part for scanning, observe the scan, transform a raw cloud of points to a usable mesh, and create a model-based definition that can enable the part to be reproduced. It seems this should be an easy part to scan with such well-behaved surfaces. It turns out that shiny objects with little or constant curvature are among the most difficult. To simplify post-processing, white powder was applied to the surface to provide a matte finish, and targets were drawn to aid in registering multiple scans. The scanner used for this project is the Artec Space Spider. This is a metrology-grade scanner that can capture color and texture and features as small as 0.004 of an inch. This handheld scanner is specifically designed for smaller parts. To make the scanning process easier, the part has been placed on a turntable and used with software that will couple the scanner and the turntable. This technique involves making multiple passes over the object and then gluing them together during post-processing. The technique to capture the points is similar to spray painting. The scanner is slowly raised and lowered, remaining perpendicular to the features. During capture, I will watch the screen, paying attention to the real-time display of the acquired point cloud, as well as a diagnostic display that indicates the point density being captured as a function of distance. The optimal distance for this scanner is about a foot. So you can see that this is not the scanner you want to use for larger parts. Now that the point cloud has been captured, it will be post-processed to remove unwanted points such as warts, points resulting from scan noise, and to ultimately generate the mesh. Artec Studio has utilities to do this. The turntable can be removed by a single swipe which will identify all the points on a plane. Another utility will remove all points that seem to have a random pattern. For this part, multiple scans were required, and now they need to be aligned. This is done by identifying at least 3 reference points on each of the scans, and then letting Artec Scanner do its thing. A well-defined point cloud now exists, and the mesh can be generated. The power of this software is it can interpolate across small gaps. Notice that our scanner was able to capture a portion of the internal threads. At this point, the mesh can be used as is, or to generate a solid model. Here we see the point cloud. Now, the mesh created to the points. And now the mesh itself. The point mesh was used to define a solid model of the as-is condition of the part. It appears this part can be modeled as a solid of revolution. The first step is to create a cross-section by intersecting the mesh with a plane. The resulting polyline is used to generate primitive wireframe, such as lines, arcs, and B-splines, which can then be revolved to build a solid. Another part we scanned was a bolt. The mesh was used to create the helix for the threads, which when joined with the head forms a solid model of the bolt. This bolt geometry can be subtracted from the hitch to form the internal threads. It can also be used to create a basic model. This model uses the mesh to develop a parametric definition which can then be modified to define the inferred as-designed solid geometry, as well as the feature controls which can capture much of the design intent. One of the features is flatness. This can be obtained by analyzing the point cloud that makes up the bottom surface of the hitch ball. The deviation between the highest and lowest points of the bottom of the hitch was used to determine the actual flatness of datum feature A. Based on engineering judgment, this 1/100th of an inch will be used in the model-based definition. Additional design intent in the form of datums and feature definitions can be placed into the model in accordance with ASME Y14.5 as per Mill Standard 31000. This model can then generate neutral file derivatives such as STEP for long-term archiving. Now that we have a 3D model-based definition with captured design intent and product manufacturing information, we can validate the model by creating a plastic part to check size, producibility, and fit. Here you see the original part and a prototype made of plastic that was manufactured in the field in under 2 hours. You can call or email me for more information about the model-based definition, digital thread, generating a technical data package using scanned point clouds, or technical data in general. I am Ben Castle and can be contacted by voice at 703-917-7249 and by email at bcastle@lmi.org.